And this is topic 2. Momentum is conserved. Now, this topic should really appeal to people who have a strong sense of organization. So, like, people who find accounting to be fun and exciting and just meeting their needs. Well, this is for you. Okay, so if you have any object, let's just say here, we've got this object. Let's always go with a standard ball. This ball contacts another ball. Let's say it's a red ball. Here it is. These two were once moving in opposite directions, and they come into contact, they collide, and they impart an impulse. So on this ball right here, we've got a force. We'll call this one B, and that one A. No. Oh, I'll just use a closer color. I'll use this color. Call this one A. So this would be the force on A due to B. And on this ball, as soon as they come in contact, there will be a force on B due to A. So on this ball over here, there is a force on B due to A. I'm just going to draw the A in first so I don't have to switch back and forth. Force on B due to A. Okay, now this is in an isolated system. Nothing else is impacting these two balls except for themselves right here. They have just come into contact here. I guess you could say, like, the frame before this, they were apart from each other, and now they're in contact. And then after this, the next frame in this motion, these are going to go off in opposite directions. So there'll be a force on A due to B, and there'll be a force on B due to A. Now this is just like Newton's third law. Every action has an equal and opposite reaction. So what we can do here is we can say that the force, here in this case, the force AB, I'm not going to mess around with all of this changing color right now. The force AB is exactly the same, but is in an opposite direction. Remember, these are vectors, so it has to be negative. It's the same as BA. You could rewrite this if you wanted to as, it does not matter here. You could say the force BA is negative AB. It does not matter. These two statements, they don't matter. So it doesn't matter which one you choose, they're equal to each other. So in this case, the force on A is a negative force of BA, and the force of BA is a negative force of AB. So they're just negative forces of each other because they go in the opposite directions. That's what this negative means. It's just talking about the direction. The magnitude is the same. If we did not care about the direction, it would just be the force AB equals the force BA. But we do care about direction since it's a vector, it's a force, so we need that negative there. Okay, now this is just in a one-dimensional system. I also should say that. It's not a two-dimensional system, so that means it can only go, this movement right here, this law is only, and the thing I'm going to show you here is only true if these things are going in exactly a straight line here. And they collide and they go back along that straight line. If they're moving at angles and they're colliding, then holy crap, we've got other things to consider. But I just want to show you this, because this is the easiest way of showing you this kind of relationship and the conservation of momentum. So, you got this. Great. So, we could say, the time as well. The time is equal for these things that are in contact with each other. So we could say the force BA times the time it's in contact, and will equal the negative force of AB times the time it's in contact. Well, what this is not a big step here. Okay, the amount of time that they're in contact is the same, so this should be equal as well. So this is not a big step here. You should be able to accept that pretty easily. So what this is this should look familiar. This is an impulse. So this is the force BA Oh, shoot, I shouldn't have written that. Let's just do this. This is the change of impulse for A, or for B, and this is the change of impulse. I'm sorry, the change of momentum for A. Did I do that on the right side? No, I didn't. I'm sorry. I'm just going to make sure that they line up with the balls that are above them. Okay. This is the change of impulse for A, and this is for B. B is this ball over here, and A is the other ball. Okay, so this is B, and that's A. So, oh, right, and this is negative. The negative change of the impulse. Okay. So far, so good. So what is the change of, I keep on saying change of impulse. What is the change of the momentum? It is the momentum of A, the final, minus the momentum of A, the initial. And this is the, well, the whole thing is going to be negative, and it's going to be the same kind of formula. The final for B minus the initial for B. Okay, great. Now, something that's really nice here that I'm going to do is I'm going to rearrange these so we can get rid of all these negative numbers. So all I'm going to do is, first I'm going to distribute this negative. I'll do that really quickly right now. So minus PBF plus PBI will equal this. I'll just rewrite this. Okay, it's going on a little bit of an angle here. Now I'm going to just add this term over here to this side. So it's going to be, and I'm going to add this term over here to that side. So I'll do that all in one step. So it's PAF plus PBF equals PBI plus PAI. Okay, this is starting to get a little significant. So this means the momentum, the final momentum of A plus the final momentum of B should equal the initial momentum of B plus the initial momentum of A. So that means if we're just considering this system here with just these balls, nothing else, the momentum that they have before added together will equal the momentum that they have afterwards added together. Holy crap! That's amazing! Your head should just explode. Holy, this is weird. The momentum before equals the same momentum afterwards. So the total momentum before equals the same total momentum as afterwards. That means momentum did not change. The total amount of momentum stays the same. So another way to say that the total momentum, I'm getting too excited here. The total momentum stays the same. Stays the same. That means that momentum, fancy way of saying this, momentum is conserved. Period. It does not change. And this is true for the entire universe. By the way, it's true for the entire universe. It's true in this little scenario, and it's true for everything. If you count up every little particle in the universe right now, all of their momenta, that's plural for momentum, count up all the momenta, and then just a fraction of a second later, the momenta is the same. The total amount of momentum stays the same for the universe, the entire universe. So if you slow momentum in one case, somehow it's got to be replaced. That's just the way the world works. Momentum stays the same. But we're not through yet. So this is great. This is fantastic. You can put this as a tattoo on your arm. But we can also expand a little bit more. And this is what we're going to be using for the problems today, over and over and over again. You're just going to need to keep count of all the variables. And there are tons of variables here. So let's get ready to go. It's going to be the momentum right here. Let's just put it in M and V form here. So the momentum equals the mass of A times the velocity of A, and that's the final velocity, plus the momentum of B times the velocity final of B. Okay, now that equals the momentum of A, and this is the initial velocity of A. You can write it with, this is weird, but oftentimes text writes it as this, not the U. And you can also do this for B, mass of B, and that's times the velocity for B, the initial velocity for B. Okay. Now, let's say you have lots of information and you just want to find one of these terms. Well, it just turns into an algebra problem. So, for example, look at example number 1. It says a 2.1 kilogram ball is thrown at Mark's head at 3.4 meters per second. So let's just say that that's the initial velocity and initial mass of a ball. So you've got that, and you've got this taken care of. Mark's head has a mass of 5.1 kilograms, and it was at rest when the ball collided with it. So that's the initial velocity would be 0, and the mass would be 5.1. Okay, and then afterwards it says, what is the velocity of Mark's head after the collision? Oh, I'm sorry. Mark's head had a mass of 5.1 kilograms. It was at rest when it was collided with it. Okay, those are those two. And what is the velocity of Mark's head after the collision? Hold on a second. What is the final? Did I miss something here? I think I might have missed something here. Hold on a sec. This should have more information in the problem. That's what I'm missing. Let's see. The ball has a final momentum. Did I tell you what the ball's final velocity is? Let's just assume that the final velocity is 0 for that problem, unless it's otherwise stated. In the version that I have right now, it says that there's nothing to be left. There is no final velocity for that problem. So let's just say that if we're using A as the ball, then there would be no final velocity here. So that would be 0. And the mass would then cancel out as well. The same mass is there. So all you need to find then is the final velocity of Mark's head. So all you need to do here is rearrange all these variables. I'm going to do that right now. I'm just going to rearrange the variables. So it'll be, this is the same for every problem like this. It's very, very similar. Now we divide, or we subtract first. We subtract the MA, VAF, and then we divide the whole thing by MB. And we'll get velocity BF. So all of these problems are very, very, very similar. All you have to do is figure out what variables are given to you, keep track of every single variable, and just solve algebraically like this. You should be fine. Good luck.